Okay, so now it's recording. So last time we stopped at the Weierstrass uniqueness for the Vlasov equation, Vlasov system based on relative entropy. So this is our starting point for relative entropy method to the mean field limit problem. I don't want to spend a lot of time on this since this is already the fourth lecture, and we need to talk about the two new methods later, maybe next week. But I will try to finish relative entropy method in today's lecture. It will be slightly fast, but it's research oriented. So if you have a question, you can email me. I mean, even after lecture 6, there are total 6 lectures. So if we haven't finished, I can still do some recording. So actually I plan to give a one semester course on this subject in Peking University. And this is like short version of the topic course. Okay. So so last time we already, right, we have two, let's assume we have two solutions to Vlasov systems. So this is the Vlasov system. F is smooth solution or strong solution. F tilde is a weak solution, but we require this weak solution dissipates entropy. So so which means it satisfies the following entropy inequality. Okay. So if F is strong solution, so here is classical solution. It's not inequality, but just equality. Okay. So we can just do the computation. And last time we already did all the computation, and you can check that. So let's just start now on lecture 4. Okay. So we use relative entropy HT to compare two solutions, F tilde, which is weak solution, F is classical solution. So the relative entropy HT satisfies the following inequality. And the last term here, right? Last term here is, it comes from 3 terms, and we do integration by parts, and we can merge them together, get a positive term, and there's a minus sign here. So we can just throw this term away. So we just get this part, both for the deterministic system and stochastic system. So that's the inequality that is for the relative entropy. Okay, so here R actually is a discrepancy term. So this is the force generated, the force field generated by the distribution rho tilde. This is a force field generated by a distribution rho. So R basically captured the discrepancy, but it's a weighted discrepancy. Okay. And so what we need to control is just this term, Okay. So so a very easy, almost trivial observation is the following. So if we change this F tilde, we change this F tilde to be F, and so we just compute the integral here. Let's, for simplicity, just this is integrate from RD to RD. Okay. Okay. So if we just right, so we multiply F here, right? So let's use it. We multiply F with this term, so we get divergence, not divergence, gradient V of F. So integration by part, right? So since the derivative is only one V, the derivative is on velocity variable, right? On V variable. So integration by parts, of course, we need some certain assumptions, but that's not a big deal. Integration by part will gives this whole term vanish. Okay, so to control, right, this term, we can plug in a 0 term, right? We just do this computation, right? Since the contribution from this term is 0, right? So we can just do all the trivial estimate. So here we just using the trivial estimate, we're using the L infinity norm, right? We pull out the L infinity norm, so we get this term, okay? And we just put the absolute value everywhere, right? Put the absolute value here, put the absolute value here. And so this is just easy, this part is just easy computation, right, from the definition of convolution. So we can pull out the L infinity norm of K. So then, so this part is L1 norm, L1 norm. So L1 norm of a spatial density is controlled by L1 norm of the phase space density, because it's just integral, right? So here, just to remind you, rho theta is just the integral of f in velocity variable, right? So rho is the integral of f in velocity variable as well. Okay. So we can wrap up all the commutation here. So we can get the integral type estimate for relative entropy, HT. Okay. So so this is K. Okay, so we have this term. We have this term, and integrate with time s. Integrate with time s. This almost up to now. This is just a trivial estimate. You can do that by yourself. So I do a little bit quick. Okay. So in the end, we want to get a estimate, get a control on HT, right? But now, right, so here, so we expect there will be terms, HT, right, some terms involving H from this part, right? Okay, so this, so if we ignore everything, right, for instance, we have the following, if you know the Caesar-Kubank-Pinsker inequality, so you have two density, let's say F and F tilde. So this is well known. So this is well known. So this is like L1 norm of two densities. A probability density can be controlled by the square root of their relative entropy. But here, like we can use the classical CKP for the first term. So the L1 norm can be controlled by the square root of HT. Basically, there's a factor 2, square root 2 there. But this term is different. Why, right? Because it's not just L1 distance. So there's a weighted term. This is the weight. But very luckily, there are already several work, right? There's some work in weighted Caesar-Kubank-Pinsker inequality. In particular here, we use the inequality proved by Bolli and Villani. So the index here is just the number appearing in their paper. Okay. So they control the following, right? I just apply the first inequality. So here phi is just a scalar function, and mu and nu are two probability measures. So the right hand side, sorry, the left hand side is just the weighted total variation distance. So you can think, right, if both of them have density, this is 1/2 of the L1 distance. And you can control the total variation distance by relative entropy. So here is weighted version. It's not exactly square root of H. So they have the weighted terms, right, given by the exponential integral of the weight, and there's also extra terms. I just we just use the first inequality, right, this inequality. Okay, so if we apply this inequality, right, so if we do some rescaling, because we in our assumption, we assume this number. So this is our assumption, but so we assume the integral of lambda f is just a constant of this, the gradient v of log f is integrable against f. So this is our assumption. We assume this is finite. I guess this is called theta f. Okay, so we do a little bit scaling, but anyway, we can control, right, under this assumption, we can control the weighted L1 norm between f tilde and f by square root, basically square root of the relative entropy between f tilde and f. But there's a different term, right? There's a high order term. There's order 1/2 h as well. Okay. Then, right, so then for this part, we just use classical serial Kullbaum Pinsker inequality. So we can end this estimate. We can end this estimate. Okay. So if we assume, right, let's say we're starting from the same initial data, or the initial distance between f tilde and f are very small, let's say h0 is less than 1 or something. So if h is relatively small, right, the high order is smaller. So we can just get this. We can just get this. And we can just using integral type Grunwald inequality again and get the estimate of the relative entropy. And you can see, right, so this is a L infinity norm of the interaction kernel K. And this is our assumption on the smooth solution F. The smooth solution, you should be able to take derivative, and the derivative in velocity direction is exponential integrable. And you can in particular check, right, if f, right, is Gaussian, like Maxwellian, and so so this is true, right? So you can find lambda f such that theta f is finite, right? So this class, of distributions includes Maxwellian or Gaussian type distribution. Okay, so this computation is very easy, right? We just, the only slightly difficult part is we use the weighted version CKP inequality. Okay, and this gives us the scale, right? The scale of k, right, which is L infinity. So then, right, we try, can we like compare like particle system with Vlasov system, and also assume the interaction kernel K is L infinity. So does this type of estimate also works? And the answer is yes, and this motivates the relative entropy methods in mean field limit. Okay. So, but there's a problem. So what's the problem? The problem is if we only assume, let's go back one step. So if we only assume the interaction kernel K is bounded, so what's the meaning of the particle system? So this is a particle system we considering in our first paper. So so here, so K is only bounded. So classical well-Posness for like ODE or SDEs, you need K is Lipschitz. You can relax this assumption. For instance, you can consider you give a meaning of ODE or SDE, like what has been done by Dipernat, Lyon, and Ambriso. So you can relax assumptions. For instance, you can assume K is BV or in some sublevels spaces, and you can still give the meaning of the SD or ODs. But our assumption K is too weak. So it's just only bounded, right? You cannot apply like Dipernat, Lyon and or the Ambriso's result. So what we use is the following. So so we consider, we are not considering the particle system in the flow sense. So we consider the statistical sense of the particle system. We consider the evolution of the joint distribution. For instance, for the second order system, I just showed you. So this is Fn. Fn is the joint distribution of n particles in phase space. So this is the Liouville equation. So under the assumption, very weak assumption of the interaction kernels, we can only have we can only have weak solution. So in particular here we use a weak solution, right? So which is a solution in distribution sense, but also it dissipates the entropy. So we need this, right? Because we need dissipates. We need the entropy bound later, right? Because we want to use relative entropy to control everything. So we need the weak solution dissipates entropy. To get that, we need right initial data has finite entropy and have finite moments, for instance. This can be done by approximating the interaction kernel K. Like we can approximate this K by K epsilon, right? K epsilon equals to K convolve some modifier, and then you send epsilon go to 0. Okay, but this can be done, and we are using weak solutions, and we don't have the uniqueness of weak solutions, but later you can see no matter what weak solutions you used, it will always be close to the limit, the target in the marginal sense. Okay. I won't talk too much about this part. Okay. So now let's talk about the method, the relative entropy method. Okay. So we use the scale relative entropy. So usually, right, we compare two probability density, right? Like before, right? We just, let's say we have two density, right? So this is KL divergence or relative entropy. This is positive, and it can quantify the convergence. Let's say if Fn converge to, let's say this converge to 0, right? So then Fn converge to G, right? In some sense, and actually in strong sense. But now we are comparing like n particle system to the limit. So so here we need to take the relative. Okay, so we need to scale the relative entropy. So why? Okay, so it's like that. So you can so the idea is like following, right? So you can check that. So for instance, right, if we take rho n, right, if we take rho n to be, let's say to be f to n, right, it's the tensor product of f. So if you so this rho n, right, might be quite far from, let's say, so here let's take Gn is G tensor product n. So it's just n copies of G. So so the first one is like n particles, IID particles. Each particle satisfy distribution F. So the second is like we have another IID random variables, and each of them, let's say we have X, Y, so Xn, so IID, and each of them satisfy the law F. Right, second one is Y1 to Yn, and each of them satisfy distribution G. Okay, so rho n Gn can be quite far. So let's say F minus G, let's say in some sense, probably very close. So now, right, if you compute this the distance between rho n and gn, right? So you can find this is just if you do this computation. So if you take a tensor product, f tensor product, g tensor product, or you take the relative entropy. So then there's a factor n comes out. Okay. So in order to bring everything in order one, right, we need to take the we need to do the normalization. So otherwise, this quantity might be large, but let's say in order one, but you still have the propagation or chaos result. So you still have the system, you still have a particle system will be approximated by PDEs, but rho n and gn are actually are far. Okay. So we use this, we use the scaled relative entropy. Okay. Let's say, that's right here. Okay, so this normalization, 1 over n brings everything to order one. Okay. The following property is very important. So once we control, it's called monotonicity, or basically it's come from the subadditivity of the relative entropy. And so if you control relative entropy and dimension n, right? So this is the full relative entropy, right? Like we defined before. This is the relative entropy between k marginal and rho bar k. Okay, so okay, so this seems very very easy to prove, but you can try to prove that. You can find a proof in my thesis. Here we need to use the property rho n is symmetric. So here we need to use this is symmetric probability mirror. So the relative entropy and n dimension will control the relative entropy in k dimension. And the following is just a classical CKP inequality. So this one, because here when I write HK, the relative entropy in k dimension, so it's rescaled one. So if we multiply k, right, so here is just rho nk log rho nk rho bar k. And here is L1 distance between two probability mirrors is controlled by square root 2 times relative entropy. So it's classical Caesar-Kuban-Pinsker inequality. So here I just give you three inequalities, but these three inequalities give you, right, why relative entropy can be used as a quantity to measure convergence. Can be used in propagational chaos or mean field limit. Okay, so let's say we assume initially we have a vanishing sequence. So let's assume initially we have a vanishing sequence. So rho bar 0 is initial data for PDE, and rho n 0 are initial distribution for particles. So if initially, usually we assume initial data, initial quantity is small, right? Otherwise you cannot do that. So assume this is small. So if we can show at a later time, this quantity, right, is also small. This quantity is also very small as n goes to infinity, right? Then we can get the convergence of any k marginal in L1, right? So that's the idea, right? That's the idea. So once we obtain a sequence, of the relative entropy, so we can obtain a strong convergence from any k marginal towards the limit. So since we assume stronger assumption initially, right? For instance, we assume initial vanishing sequence of relative entropy, and we expect actually we can get stronger convergence compared to Keck-Scales, right? So let me just remind you, right, what we did last time. Right, so this is Keck-Scales, right? So so Keck-Scales only work, so means like a weak convergence. So here, the K marginal converges to the limit is weak convergence. So weak convergence means if I give you a test function which is continuous and smooth, so you test against rho bar nk, it will converge to the expectation, right? Those, let me just write down. So right, so the classical, so Keck-Scales. So Keck-Scales means the following, right? So rho nk is really, right, if you take any k marginal, this converges to k weakly, so weak convergence, or convergence weakly. So this means, right, just a standard minimum, right? Give you test function, that's a phi1, x1, phi n, phi k, xk, right? You test against rho n k, dxk. So this will converge to, so here, let's say the underlying space is E, maybe just the Euclidean space. Okay, and it will converge to phi1 x1 phi k xk rho bar dx1 rho bar dxk, right? So this is weak convergence. Weak convergence definitely is weaker than strong convergence, right? So weaker than this. Right. Okay. 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 So this is what we need, right? So let's just see one example. Okay, maybe just to say one more word, one more sentence. So, see, in 1999, so Benoist and Zettoni used the same things to study a different problem. So they also use the monotonicity of scaled relative entropy. Okay, it's not so these all three estimates are not novel, right? So it's known for in the community for a while, and people use these things to do other things, to do yeah. Okay, just to give you one example of the result. Later, I will show a very specific interaction kernel, the Biot-Savart kernel. So I will show this kernel, the main steps of this example. But the main theory I show here, right, it's much general than Biot-Savart kernel. And you need to use a lot of things like entropy analysis and integration apart. So the proof can be very complicated, but I don't want to do that. So I want to just use a specific example, the Biot-Savart kernel, and explain the idea. So as I said, right, so this is motivated from the weak strong uniqueness things. We assume the limit solution rho bar here. We assume the limit since rho bar is very smooth. But we assume the interaction kernel can be very rough. So if there exists positive noise, so sigma is the strength of noise. So if the system is stochastic with strictly positive noise, the strength, I mean, so you can treat the kernel, which is in some Sobolev negative Sobolev space, and the divergence kernel is also in negative Sobolev space. And we can give the explicit convergence rate of the relative entropy. Basically, this is the main theory. We can propagate the relative entropy, right? So as I said, right, initially, right, we can even assume the IID. We can even assume Rho, right? If we assume initial particles are IID, okay. So this is IID. So then the initial relative entropy is 0. So in this specific case, we can get the later relative entropy is in the order of 1 over n. So that says, right, the convergence of the K marginal is in the order of 1 over square root n by CKP inequality. So this is believed to be optimal. Okay, so the idea, I will show you the idea using a specific example. Yeah, okay, the idea is very simple. It's like we derive the evolution for the relative entropy and try to control the relative entropy. So like before in the Weak-Strong uniqueness argument in the Vlasov system, so we need a CKP inequality. But the rule played by CKP inequality before is replaced by some large deviation type estimate. Okay, so this is our main goal today. Okay. Yeah, I will just skip that. This method can treat a lot of examples. For instance, you can treat a purely deterministic system, or some vanishing viscosity case, or non-vanishing viscosity case. You can see our paper for more details, but let's just focus on very specific example. And so this is a relative entropy method, similar idea. So in particular, you can see the Hongze-Yaw's paper in study of the hydrodynamic limit of Gisenberg-Landau model, and the Sarfati's study similar works. I mean, they are similar in spirit, like based on Weak-Strong type argument, based on the evolution of some functional. So actually used in a lot of places. Okay, but to study the mean field limit for singular kernels is first introduced by my advisor and myself, Pierre-Emmanuel Jaban and myself. Okay, in our several papers. Okay, I will talk about the proof, the ideas later, but I want to show you the mean field limit of propagational chaos result for the Vlasov system, which I used as motivation. Okay, so again, we can assume K is bounded, and we assume the limit function is very nice. Okay, so FT is in very nice space. And in particular, it satisfies the previous assumption we used. So the gradient V of log F is exponential integrable. So under this assumption, and also we need some uniform in N as bound for initial data, for initial distribution. So this is some moments bound for initial distribution, Fn0. So Fn is the, so Fn T is the joint distribution. So in the phase space, right? So this is the second order model. Okay. And okay, the main result is the same. We can propagate the relative entropy. And okay, you can see, right? This is the quantity, right, all appearing here. Okay, so yeah. So I just mentioned, right? So so this result is parallel to the Weak-Strong uniqueness result, for Vlasov system. Okay. So now let's talk about the basic idea. I just want to give you a complete proof for this case, for the 2D Navier-Stokes or 2D Euler. 2D Navier-Stokes or 2D Euler. So which means here is the title of the section. So which means the interaction kernel is singular, but the singularity is not very strong. The singularity is in the order of 1 over x. Okay, so this is called Beer-Szafir law. Okay. Okay, so let's do that. So if you have questions, you can just ask or type in the chat. Okay. So let's make another assumption. Let's assume sigma n is all equals to sigma. So the original particle system. So let's just remind you, right? So so this is the original particle system. So usually we put so this. So Wi are Brownian motion. So Wi are Brownian motion. So K here you can just choose a Beer-Szafir kernel or other kernels. Okay. So as I said, right. So we are starting from the Liouville equation. And so from the particle system, right, we can using the Ito formula, right? Just to write the evolution of the rho n. Okay. So using Ito formula, you can get that. Okay. And the expected limit, right? So the expected limit is just a partial T rho bar plus the aggregation diffusion type equation. Okay. So now, so we just want to evolve the relative entropy between rho n and rho bar n. So rho bar n is just n independent copies of rho bar. You can just do that, right? Just take you just take rho bar n as the n product of rho bar. So which I think is just so maybe just right here, right? So rho bar n dx1 to xn is just the product xi, right? So we can derive the evolution equation for them. So I write below for the computation, but you can do that very easily. Okay, so basically we compare two systems, right? So the first one is Liouville equation. The second one is not Liouville equation, it's a modified Liouville equation. It's the evolution equation satisfy rho n bar. So basically just the n copies of the limit. And we want to compare rho n and rho n bar. Okay. So the following is just a little bit computation. I just want to point out, right? So this is Liouville equation, right? This is Liouville equation. If we write it in this way, right? This is the vector field in very high dimensional space, right? This is a force field, right? Force field. So if we write the evolution equation for rho n bar, right, it's the same. But here, right, the velocity field is V bar, right? V bar is also a vector field in very high dimension. And basically we are just comparing two different Liouville equation. Okay. Okay. So here I skip a lot, and the computation, the way to write this is not very precise. So like before, as we did for the Vlasov system, you need to use the meaning of the weak solution, right? So for instance, here rho n is weak solution. So rho n is called entropy solution, and rho n satisfies some entropy inequality. And you need to do that, right, to make this precise. But if we just do in informal way, and we just take the derivative of relative time derivative of relative entropy, and there are a bunch of terms we need to control. Okay, and so this is the final formula, and you can look at our paper for the complete computation. But basically, there are two terms in the last step. As before, what we did in the Weak-Strong uniqueness for the Vlasov system. So this actually is a module. Okay, it's should called how to call this term. So for instance, right, we know this, right? If you take the time derivative of entropy, so you will end up, right, with a Fisher term if there's a Laplacian involved. And here, right, it's not a Fisher, it's not just entropy, it's a relative entropy. So if you take time derivative, there's a relative entropy, there's a relative Fisher information term, right? This is like what the term appearing here. But this term has a sign. At least if you choose sigma n equals to sigma, we can easily get a term which has negative sign. Okay, so this term, so since we want to treat like both, like for instance 2D Navier-Stokes and Euler, we can throw this term away, right? Because right, sigma can be even taken to be 0. So let's throw this term away because this term is negative. And we only need to control the following term. We need to control the following term. I'm a little bit cheating here because if you recall the definition in the particle system and also in the Liouville equation, you will see, right? You will see right here, so J is not equal to I, as in the force field right here. So J is not equal to I, so there's no self-interaction. Like particle I only feels the interaction from n-1 particles, other particles. But believe me, right? So here it's not a big deal. At least in this scenario, for instance, K is bounded, or you can use in some way to make it a bounded case. This is not a problem. You can, so usually we make a convention that so Kxi minus Xi equals 0. So if we have two indices, right, in the summation are the same, right? In the diagonal term, the index I and index j are the same, right? I equals to j. So actually there's no contribution in this term. So there's no this term. So we made this convention. Okay. This is not a trivial thing, but it just didn't become harmful, right? When we treat some bounded regime, because so I write here a little bit. So for instance, right? So we have summation both in I and J, right? And then we normalize by 1 over n squared, right? So this a priori is in order 1. So if everything is bounded, so consider or not consider the diagonal term doesn't matter a lot, right? So why? So because we only have n diagonal terms. So if each diagonal term is bounded, right, so in order 1, so if you normalize by n squared, you get a very small quantity. It's in the order of 1 over n. So it's like what I write here. So this is fine. But if you are considering very singular kernels, right, this actually is a very technical part. I will try to explain this in next week's lectures. Okay, but here is not I point out this cheating, but this is not harmful. Okay, so phi, right? So phi, if you do all the computation, we will find this phi xy is given by okay, this term and this term. This is just the difference of like this is limited system, right? This is the interaction. This is the limited system. This is the interaction particle system, right? Okay, and this makes sense. Okay, and a trick, right, which is used in a lot of places called symmetrization. So we can symmetrize this phi. So we can get more regularity. Right? A very easy way is just okay. We take phi xy and plus phi yx. We exchange the order and take the average. So so the sum doesn't change, right? But when we do that, we get some very nice terms. Okay. So the next page, right? This page is a commutation, but it's not very important. The bounded terms here, right, is just this term, these full terms, and so maybe not a bounded term, or we take k to be if you take k is the Beer-Savart kernel, right? This is singular terms, right? But since we did the symmetrization, if we assume rho bar is nice, so here, then this term x like x minus y, right? C, right? C is the Lipschitz constant. So if k x like 1 over x minus y, right? It's not very singular. The singularity is in the order 1. So we can show phi xy is bounded, right? So for instance, in the if you choose k to be the Beer-Savart kernel, so phi xy is bounded, right? In particular, in the Beer-Savart kernel case, right, the divergence k is 0, right? The Beer-Savart kernel has has divergence free. If you take divergence, you get 0, right? So this term, so the last term doesn't disappears. Okay. Okay. So now we just have we just need to control this estimate. Okay. Okay. If you observe this, right? So let's say we can make an even stronger assumption. Let's say phi is infinity, and this works for Beer-Savart kernel after we do symmetrization. Okay, but if we just do like a trivially estimate, right? So here we have n squared term summation, and it's normalized by 1 over n squared, right? So the expectation here is in order 1 a priori. But if this is order 1, so we are dead, right? Because we assume initially IID, so with time the relative entropy becomes in order 1, and you cannot get propagation or chaos, right? So we must use some more information, right? Okay, so so here you can check, right? Even without the symmetrization, so the original choice of phi xy have 2 cancellation rules. So we call these 2 cancellation rules, or 2 mean 0 property. So this actually is very important in our main estimate below. I will show you the large deviation type estimate. Okay. So what's usually how to estimate these terms? Usually people use a change of mirror idea. So like the following inequality, which has many names, but let's just call it Gibbs inequality. And so what Gibbs inequality really do? Right. So here is just checking these 2. Just checking these 2 cancellation properties. So what is Gibbs inequality, right? So we want to control some terms, right? Some expectation against distribution Rho-n, right? Rho-n is a distribution, right? It's a probability measure, you can say. So we want to control this quantity, but we don't know a lot of information about Rho-n, because Rho-n might be some weak solution, some very bandgap we are not very familiar with. So we can change our reference measure. So natural idea is change Rho-n to Rho-n bar. So Rho-n bar is tensor product, right? Let's say it's tensor product of rho bar. We have n copies of rho bar. It's just IID data. Right. So in probability, there are many techniques you can use for IID distributions, right? IID data. But here we just change Rho-n to Rho-n bar, right? So we change this Rho-n to Rho-n bar, right? But it compensates with exponential, right? So here it just some scaling, right? It doesn't it's not important at all, right? So we just put a factor here, put a factor here, put a factor here, put a factor here, right? That's not very important. So yeah, so really important things is the following, right? So it's phi x, right? Phi x rho n, right? So it's rho n log rho n rho bar n plus rho. So this is the inequality we really used, log rho n bar exponential, so nx. So this is what we used. Let's put the n here, right? And since we want to put 1 over n before the relative entropy, let it to be a rescaled one, right? So we put some factor there, right? So what we used is really this inequality. This is called Gibbs inequality. This you can find proof in a lot of places. Basically, it's just a JSON type inequality. It's a global version of Young inequality, right? So it's called Young inequality or Fraser type inequality. It's kind of this type of things, right? So xy is less than phi x plus the dual of it. But this is just a 2 point, right? For the integral, you have the similar one, yeah, which is just this. By choose phi x as like exponential function, for instance. Okay. Okay, so we use Gibbs inequality, right, to control this term. This is, let's call this phi n. To control this term, we change. We use a change of reference. We get one relative entropy here and get one more term here. Okay, so here we have one factor here. We have 1 over n here. So if we can show this quantity, the log of the exponential terms is in the small order of n, is in the high order of n, so then we actually can get propagational chaos. Why? So because now, right, so this term, right, this term is controlled by, can be observed by a Grunwald, right? This can be observed by Grunwald. Then you get a high order term, a small order term. So you can get propagational chaos. You can get relative entropy is very small, and you can get a propagational chaos. So this is our goal. Okay. In a very specific setting, let's say phi is bounded and the infinity norm is small, but that's not very important because you can change the parameter. So if phi is bounded, we actually can show by choose eta here to be very small. This quantity, right? This quantity is not only in the high order of n, actually is uniformly bounded. So this is our first main estimate. So we said the following. We said the following. This term, given eta, given phi is bounded, eta is small enough. But in order 1, this is in order 1. This is in order 1. So we can get everything, okay? Okay. So this is our main estimate. We call it uniform in n large deviation type estimate. Okay. So if we assume, so here phi in our choice, phi satisfies the following assumption, and these 2 assumptions are very crucial. So we got 2 cancellation rules, right? If we integrate with the second variable here, if you integrate with the second variable, you get 0. So if you integrate phi xy with y, right, against rho bar, you get 0. If you integrate with x variable, you also get 0. I checked the above here, right? You can check that very easily, but these are very crucial. We need to use these 2 properties repeatedly, and so we can get the estimate. So this is our phi in this particular setting. This is our phi. So you can check, right? If you integrate with rho bar y, with y variable, so you can get 0 just by the definition of convolution. So if we integrate with the x variable, right? So the first term becomes this, and you can use the integration by part, and you just get the negative term of the second. You just get the opposite terms which are appearing in the second term. So you get 0. So basically by integration by part, you can get one cancellation in X variable. By definition of convolution, you can get another cancellation. So this is 2 cancellations. So if phi is bounded and less than some critical value, C0, so then the crucial terms we need is uniformly bounded with n. Okay. So since phi has these 2 properties, 2 cancellation properties, right? So this is another way writing of the sum, right? So here, right, if we use empirical measure mu n of the configuration x1 to xn, right, we can using the empirical measure mu n to represent the configuration x1 to xn. So the sum can be represented by integral against empirical measure in double form, right? Double integral of the empirical measure. So using the 2 cancellations, right? This summation can be writing in this way. This is very important, but the importance is not as important as in the later works. But this is still very important, and I want to emphasize this, right? So this is a difference of 2 measures, and this is phi. Right? So phi is some potential function, and if you take Fourier, you take the Fourier transform. I mean, if you can, right? But somehow you cannot take Fourier transform then easily, right? Somehow it doesn't make sense, right? So it's kind of some phi hand, so mu n minus rho bar. It's something like that, right? So is that right? Okay, yeah. So yeah, so like it's Fatih's method is best like this, right? You using a test function phi, and you measure the difference between empirical measure and rho bar using some Fourier type norm. Okay. So in our case, right, just here, right? So since phi xy, our choice of phi, right, in the specific form, it satisfies these 2 cancellation rules, right? So if you use these 2 cancellation rules, you can just write the sum, this sum, and this way. Okay. Okay. And okay, that's why I write the second terms. But the problem is the following: the second term is actually more essential. So once if you just want to consider this term, you can just estimate that. As long as phi is set, the L infinity norm of phi is less than some critical number, so you can show is uniformly bounded in N. Okay. So this if phi here is continuous, this is just a classical large deviation estimate. I mean, there are many types of large deviation estimates. This is in particular appearing in Penrose and Bruno in 1990 papers. So, but they consider phi is continuous, but it's not satisfying in our case, right? For instance, so our phi is here, right? Our phi is here, right? So we normalize this, we symmetrize this phi. If we choose K is a Beer-Savart kernel, right? So we can show, right, this phi is bounded, but it's not continuous. So this phi, even is bounded, it can be not continuous. We cannot use the classical work. So we do this directly. So we do the estimate directly using combinatorics. I will show briefly later. Okay. So like how to connect with classical large deviations, right? So let's just spend like several words on that. It's like the following, right? So rho is a probability measure. So we can define a functional f rho, and we can find the m0. So m0 is the minimum of this functional. So if this phi, right? So in particular, in our case, this phi satisfies these two cancellation rules, we can show if phi is continuous, this m0 is just 0. So this m0 in specific case is just 0, and this recover our result. I write it here. You can see more discussions in our paper. Okay, so it's like this, right? If you send angle, so the minimum one give you the gross order. The minimum one give you gross order. So this I think this this probably in the order of E and M0, right? So if M0, you can show M0 is 0, right? So then it's uniformly bounded. And it can recover our result with the assumption phi is bounded. Okay. So our original proof, if we make a stronger assumption, so the original proof, we do it in more general assumptions in some weighted LP norm sense. But if you made very strong assumptions, so we can do that very easily. So this is our goal, right? We just want to control the expectation of the. So we write in probability way. So what's this? So it's just rho bar n. So we have IID data. We have IID data, and we want to control terms like this. So phi yi yj. So we want to control these terms. So where each yi satisfy the law rho bar, and they are IID. So those n random variables are IID. And we want to show the expectation is uniformly bounded. Okay. So later I will, and I didn't mention that, but later I will show you a recent proof by Lim, Lu, and Nolan. So they use a martingale argument to prove this estimate on the assumption the phi is bounded. And so our original proof is based on combinatorics argument, but works for more general assumption on phi. But if you just assume phi is bounded, we can do that very quickly. Right? So here just several pages. I told you how to do that, and you can do that very soon. So we just expand the exponential term using Taylor expansion, right? So E2A is controlled by just the even order terms, the even terms in the Taylor expansion, right? We're just using the even terms in the Taylor expansion to control the exponential. So we get a lot of terms. We get the infinite series. So we need to control the infinite series and to show this series converge. Right? There's no better way to do than we just expand everything. We just expand this moment completely, and then we use the cancellation property. Right? We have two cancellation properties. So we use those two cancellation properties repeatedly, and we can show so in each expectation in each alpha k, so most of terms will vanish. And so let's just say one several. So yeah, so then we can get the estimate. Okay. And so observation is the following. So important case is k is relatively small. So if k is relatively large, right? So if k is relatively large, right, this term dominant. So so of course it converges, right? You just use the trivial estimate. So here, right? So here is in the order of n, phi L infinity, right? So here is 2k. So if n compared to 2k is small or k is large, right? So the trivial estimate is sufficient. So the important case actually is k is relatively small compared to n. So we just do that explicitly. So there's a trivial case, I just skip that. And not so trivial case is k is relatively small compared to n. So in this case, we observe the following. So the indices is I1 to I2k, G1 to G2k. So as long as this double indices has a singleton, which means there's an integer appear exactly once in the double indices, so then the integral vanish. So we just need to count how many terms has no singleton, and we can count that by easy combinatorics, right? This is just in the order of this, and you can control alpha k as long as phi, the infinity norm of phi is relatively small, and you can control that. Okay. Okay. So, so that's it, right? But if we want to control the more general data, more general assumption on phi, and we need that to do more general things, general kernels. But I will skip that. Last year, there's a probabilistic proof of our main estimate done by Lim, Lu, and Nolan. Both of them are from Duke in last year. Okay. So any questions now? Okay. Okay, so I won't do this in details, but I just explain their idea. So they use a very, so this, the lemma 5.1 is from their paper. So this is a very easy lemma, but it's a very useful observation, and we use that in as well in our first paper. So this first lemma says, right, if you can control any k moments, and any k moments grows, any k norm grows, and most linearly, and so you can control. So what does this says, right? So this says if you can control the supreme of E, Z, K, sorry. So actually it's this. So this is P norm. So P norm over P is less than gamma. So this assumption is just the P norm of a random variable grows and moves linearly. So then this P norm, then this random variable has a finite exponential norm, right? So it's a trivial things using Stirling approximation. You can check that. But this is a very good observation, and we use that as well. For instance, in our results of weak strong uniqueness, I did that in the very beginning of this lecture. So we use assumption on F. Yeah, we use assumption. So this assumption. So we use this assumption, and you can show this assumption is equivalent to the following. So for each p is bigger than 1, so this norm, the p norm with respect to f over p grows and most exponentially, right? This is the same. And in our first paper, the paper with Pierre Emmanuel, the general functional analysis paper. So so the assumption, yeah. So this assumption, these two assumptions are equivalent, and in the particle system level, and it seems this assumption works better. So this assumption works better. Okay, but they're same. They're same, right? In the estimate, we use the use the NP over P, like the piece moment grows and most linearly, this assumption. But this is equivalent to the exponential moment assumption. It's essentially the same. Okay. Okay, so the first one is just to say then, right? So if the piece moment grows and most linearly, so the exponential moment is finite. Some exponential moment is finite, right? So you need, there's factor there. Okay, the second one is a very sharp estimate. It's very sharp estimate due to real. So it says the following. So if we have xk, which is the sequence of martingale difference. So what means martingale difference, right? If you sum up, right, you get a martingale. So xk is a martingale difference sequence, okay? So if you condition up to fk minus 1, so that's what this assumption is crucial. This assumption is crucial. So if you condition to fk minus 1, okay, it's basically just the martingale, right? So I don't need to say anything, right? So if you sum up the first n terms, you get a martingale, right? You satisfy all the martingale property, and LP martingale is just is LP integrable. Okay, so so this actually is a very sharp estimate, and people try to find this for a long time. They try to improve these factors, but this result is due to real. In particular, if P, right, so Sn is just the sum of the first n terms of xk. So yeah, so if P equals 2, this is just the Ito isometry. So then the inequality here becomes equality. In general, this is called Marcinkiewicz Zygmunt type estimate. And this is where is exactly use this estimate, and this gives the right proof of our estimate, and it's a very smart proof. I just explain a little bit, right? Okay, so so this lemma is just our main estimate restated, and so in order to get the exponential control, right, in our estimate, we will need to get the LP norm does not grows and most linearly, right? So this is a I think there's a P here, right? So yeah, so here should be something like P. Okay, so the idea is very simple. So we want to control these terms. We want to control these terms, okay? And this term is a sum of n squared terms, but there's no diagonal terms, right? So there's no diagonal terms, right? So no diagonal terms. There's a very clever observation, right? So we just slice, right? We take the different slice, right? We cut in the summation, right? Ij to different level, right? So this is the first level. This is the second level, right? This is the third one, right? So then, right? So we can write the summation as a new summation of dk, and dk is just this term, right? Let's say d1 is 0, d2 is just the sum of 1, 2 term, 2, 1 term, and d3 is just the sum of this terms, right? This level, right? And so those are conditional independent, right? If you condition of the first two levels, right, then you get mean 0, right? So we can use the very sharp estimate due to real twice, right? The first is like you just estimate this, and then you estimate LP normal dk. So if you do this twice, you can get the right estimate. Okay, that's the idea, right? That's the idea. Okay. Okay, so No questions? Okay, so let's spend 10 minutes talking about one more thing. So we can modify our LDP estimate a little bit, so then we can improve the previous result for more singular kernels. So the following one is a very not a very easy. It's a previous one, but we didn't publish this result. So due to a modified version of our previous large deviation estimate, type 1, I call it type 1 large deviation estimate. But since later we have better result, so we didn't publish this. So this theory tells is a large deviation estimate, but for phi, for the potential, which is possibly unbounded. So like a previous estimate, phi is bounded. Actually is less than some critical number C0. But C0 is let's say is some 1/3, for instance, right? It's less than some critical number. The L infinity norm is less than C0. Okay, but we want to relax this assumption. So somehow, right, we only need the assumption on the positive part, and we only need the negative part is positive definite and the as an operator. The phi minus is a positive definite as an operator, right? That means if you take x minus y, right, something like this, yeah. So phi minus is positive definite. It's kind of equivalent to the Fourier transform of phi minus or something like that. Okay. Okay. So let's assume phi has two cancellation rules as before. But now we remove the assumptions on phi positive. Okay. We only assume the L infinity norm on C0, on phi positive. So we remove the L infinity norm on phi, the potential itself. Okay. So, but we can still get that. And so how to do that? It's a very short proof. I just show you basically the idea. The idea is the following. So you have phi, which possibly does not satisfy the cancellation property. So when I say cancellation, that means the following, right? So I used several times. It's phi xy right? So this is true cancellation property, but possibly, right? Phi does not satisfy this. Right? Phi is just the any function, right? Any function. Let's say phi is just any function to R or scalar value or yeah, scalar value or vector value, right? That's fine. Okay. So so we can do a symmetrization of phi such that this phi satisfies the cancellation, two cancellations. How to do that, right? So this is original phi, right? So we add the integral against rho bar, both in z variable and omega variable, and we minus this. Okay. And now if you check this psi, right, the psi, which is symmetrization of psi, of phi, of our phi, right? So you can check this psi satisfies the two cancellation properties. Okay. Yeah, it's very easy to check, right? So yeah, you can do that. So now we can prove our previous modified large deviation estimate. Okay. So how to do that? So originally, right? Phi, right, equals to positive part, right, minus negative part. Okay. So so phi plus and phi minus. So we can do this. So why, right? So the symmetrization is a linear operator, right? It's a map from a function to another function, and it's linear. And since phi satisfy two cancellation property, so if you symmetrize phi itself, you get phi, right? So I mean that's easy to check, right? If phi here satisfy two cancellation property, so this term is zero, right? This is zero, this is zero, right? So its symmetrization is itself. Okay. So that's why we get, right, so phi, right, the symmetrization equals to itself and equals to symmetrization of positive part and symmetrization of negative part. So now after symmetrization, phi plus and phi minus both satisfy the two cancellation rules, okay? But a priori, phi plus and phi minus might not satisfy these two cancellations. Okay, so now we can write, right, so this is the previous summation, right? This is just a definition of phi, right? So what's this, right? Phi minus, right? So phi minus just equals to this. Sorry. So this is different, right? This is a symmetrized one, right? Symmetrized one. So if you sum up the symmetrized one, so you get the following. You can check this by the formula, by the definition of symmetrization. Okay, so so this part, right? If you sum up, since phi minus is positive operator, right? Is a positive definite operator. So this part give you a positive number, give you non-negative number. Okay, so there's only this part in the summation, right? So the exponential, the terms, right? This term, right? The expectation of the exponential, right? So we ignore the negative term, right? So we ignore the negative terms. So we throw away these terms. So this becomes less than. So we only need to control phi plus. And as long as phi plus is less than C0 and its symmetrization will be less than 4C0 because it's just a combination of 4 terms here. Right? So as long as phi plus is smaller enough, we can use our previous estimate because now these terms automatically satisfy the two cancellation rules. Right? Okay, so this is the idea of the modified version of LDP, large deviation estimate, let's call it. Okay, so we can actually, we can using a sequence, we can approximate some more singular kernels, but we cannot include, right? Just using this LDE, right? Large deviation estimate, we cannot include like Poisson kernels. So because later becomes better, so we ignored this. So we didn't explore this, but just using this and using approximation of the kernel K, and we can get mean field limit result, propagation result, just using relative entropy, and this can cover singular kernels up to Poisson, but not include Poisson. Okay. Any questions now? Okay, there's a student ask, maybe not a student, there's one person ask where you can find the notes and the lectures of this lecture series. I post everything in my YouTube channel. You can search my name, Zhenfu Wang. But later it will also be posted in Tsinghua University website. Okay, I think I will stop here because the later part is I haven't fully, so later part is starting talking about the new method. I think I will just stop here. So we can just start in talking about Safathi's Sabatier and During's method using modulated potential energy in field limit, and we will combine with relative entropy method to, in particular, we can study Peter-like Cassirer systems. But let's talk about that in next week. I will stop here. If you have questions, I can answer. Okay. So if no questions, I will end the meeting. So you can email me all your questions. So if we have time in the end, we can answer.